Hello everyone. So we are here with lecture 2 on radiation physics and radioactivity and radioactive decay will be our topic of discussion for today. Okay. So in the last lecture we have discussed about types of radiation where we identified that radiation is very fruitful for life and very find a lot of application in our daily life. Then we understood that radiation can be classified in three ways: particular wave, hazardous or non-hazardous, and ionizing or non-ionizing. In ionizing itself we have identified ionizing having a particle beams and which having a charged particles, uncharged particles classifications are there, and we have identified a number of particles as showing a charged particle also alpha, beta, gamma, alpha, beta and proton beams etc. Then we have identified that the ionization beams contains electromagnetic waves also, that means X-rays, alpha rays, but they are indirectly ionizing one. Then we have identified non-ionizing beams which are called different parts of the electromagnetic wave. So now we are moving to a section where these all source of electromagnetic radiations or alpha particles are coming. So one of the main sources of alpha, gamma, beta particles are radioactivity and radioactivity. Now let's know what is radioactivity, radioactivity decay, how they are responsible for the production of alpha, beta and different other particles. So radioactive decay. So before that we need to know about what is radioactivity is there. Radioactivity is a process through which nuclei is spontaneously emit subatomic particles. So who discovered it? So we know that French scientist Henri Becquerel in 1896 who discovered this radioactivity process. But later, after 4 years later, the term radioactivity was suggested by Marie Curie. So which was the element Becquerel find that radioactivity? It's uranium, right? Okay. Remember all those things. So originally there are three types of radiation were discovered in those times. That's are alpha rays, beta rays, gamma rays. But nowadays we know that there are, apart from these rays, there are many other can produce using alpha decay, beta different radioactive decay. They are neutrons, protons, neutrino, positrons. They all can produce using this radioactive decay process. Okay, so let's know how they are producing using this radioactivity and radioactive decay process. So we'll take each one by definition. So we have four processes in order to produce alpha, beta, gamma. Then in order to produce neutron we have a process called spontaneous emission. So in the alpha decay process, what we having is an alpha is a helium nuclei with only 2 protons, 2 neutrons. Then we have beta rays, which is actually electrons, similar to an electron. Then gamma rays, which are photons. So in a process of alpha decay, it's happening at nucleus of that atom. So when a radioactive decay happening, spontaneously emitting a subatomic particle called alpha. At that process, if you have a radium which having 222 and 88 as proton numbers, where in this representation where the X is the element or atom which having a neutron number n plus p is the proton number, and in the subscript it's represented the proton number of protons available. So after an alpha decay we'll be having another new atom. So we'll be getting a new atom with a new numbers of neutron proton number and a proton number. So along with we'll be getting a alpha. So which alpha consisted of a helium nuclei with 2 protons and 2 neutrons. So we'll be taking 2 plus 2 from the top and 2 from the subscript. Then we'll be getting this particular atom as you can see in the transition. Okay. Now the next process we will be addressing is about beta decay. How do you produce a beta particle? So beta particle is actually producing in a way is electron emission is happening. So when a nucleus is emitting an electron, at that process you will be getting an electron. So we have an indium atom. Okay. So in that we have proton numbers as 53 and 131. Then there will be a process called 131. We will be having here. What is happening is that the atom actually gaining a new proton number. Okay. So that means we will be getting an electron plus an anti-neutrino. So basically a beta decay is the process of emission of electron plus you will be getting an anti-neutron. So in all the process, as we will be discussing, you can see that there will be a clear charge conservation is happening on the two sides of the equation. Okay. So in a gamma decay process, the asterisk actually representing the atom is in excited state. So we have an atom is an excited state with a number of n plus p as 152 and 86, and it is de-excited to a ground state and 150 to 86. So it remains the same atom, but it is de-excited from an excited state to ground state by emitting an alpha photon radiation. Okay, that's how you will be getting a gamma decay. So gamma decay happens is from excited state to ground state transition. You will be getting gamma rays. So alpha and beta are particles. Gamma is the electromagnetic wave that we already have discussed. Then we have a spontaneous fission process. This alpha, beta, gamma, decay process actually considered as artificial processes, but this spontaneous fission is basically considered as a naturally occurring. There are two types of radioactive decay. You can say that one is naturally occurring, one is man-made or artificially occurring case. So spontaneous fission is considered to be a case where we produce a neutron using a natural way, so which is a spontaneous fission. The product of a spontaneous fission, so we're having a heavy nuclei in that spontaneous fission, which is split into two lighter nuclei. So these two lighter nuclei are called fission fragments. So this term I think we have discussed in the last lecture also. Fission fragments are produced by spontaneous fission. They are the lighter nucleus. A heavy nucleus split into two lighter nuclei, and it will be producing neutron also. So this is one of the way to produce neutron. There are many other way we will come across where the neutrons are producing. So this is what counted as one of the way to produce the neutrons. So this one term we need to identify. What is anti-neutrino? So what is anti-neutrino? So neutrino is the actually counted as a low interacting chargeless particle. So which having a neutrino, it's discovered in 1952. Okay, by Pauli, and later we identify that it has an antiparticle called anti-neutrino, which is actually balancing the electron emission energy. So here we have an antiparticle of neutrino to balance the energy conservation. So there will be, if you just compare the energy at the two either side of the reaction, there will be balancing to be done if we don't have anti-neutrino. So actually the neutrino emission also happening while a beta decay is happening, can be understood from that. Now we get to know what is radioactive decay. What's happening to the atom when a radioactive decay is happening. So why the radioactive decay is happening? What's happening is that a nuclei emits a subatomic particle. That's called radioactivity, right? A nuclei spontaneously emits subatomic particle called radioactivity. In that state, there will be a change in their configuration, state, change. Okay. So in such situation, so we have to say which is called the radioactive decay. So when a nuclei emits a subatomic particle, their configurations change, even identity may change. That we already understood, right? That means, for example, when a nucleus emits an alpha particle, the nucleus has two protons and two neutrons less than the original one. We identified it, right? So that means there is a change in the actual state and configuration of the atom. So in the case of gamma decay, in which the nucleus retains the same identity and all other decay transform the nucleus into totally a different one. So this process is called a radioactive decay process. So now we get to know, so I have given something here, right? So you have identified this kind of reaction earlier also. That means krypton plus electron. You have seen somewhere? So we get to know what it is, okay? So we have beta decay process, right? Okay, we have beta decay process where we identified that beta decay is happening with the electron decay. Like electron decay is there. In that process, we will be getting electron is emitting. Such process we will be getting beta. So this is equivalent to a beta decay process because beta is equivalent to electron. So this is one of the way we will be getting an electron. That means beta decay. So in another way is that we have an electron capture method and another beta positron decay method. Okay. So in the first two process it's involved an electron. In the last process there is no involvement of electron, but instead there is an involvement of positron. Positron is the positive electron which having a charge plus. Okay. Then electron capture, we are having a krypton. What is the electron capture process is that we are having a proton, that means in the nucleus. In the nucleus we are having a capture of electron that is revolving around the nucleus, and the proton plus electron will be giving a neutron. Then plus additionally we will be having a neutrino. Okay, for charge conservation. So this is a process called electron capture. Okay, how it's happening is that you can see here much detail. We have for example here krypton plus electron. It is giving another atom which is in an excited state plus a neutrino. Then excited state atom is actually converting to a ground state, the de-excited to a ground state, plus additionally there is a photon emission in terms of gamma ray. So this electron capture process is involving a gamma ray and a neutrino, this additionally a new element. So in this element itself, if you closely watching, you can identify that there is a decrease in number of protons here, 36 to 35. But there is no change in neutron proton value you cannot identify. That means corresponding to a decrease in proton, there is an additional neutron is coming here. So we are balanced with the 81 some neutron plus proton number, but we got a new atom by now. Okay, we got a new atom with the same number of neutron proton and with a less proton number. This is called a electron capture process. So there is an emission of alpha ray also can be noted in this point. Now we have a positron decay. Positron decay means that we have an atom. Okay, so this atom having a proton. This proton actually is split into neutron plus positron plus and neutrino. So this combination of positron and neutrino will actually, and plus neutron will balance this charge conservation here. So here also you can see that the number of protons and neutron number is balanced here, but the proton number is decreased, but we got a new atom here, so there is a radioactive decay process. And along with that, here we are getting a positron with a positive charge and a neutrino. So normally this positron decay happen very rapidly because there is a huge requirement of energy is required. It's close to 1.2022 MeV. So normally it's very difficult to see the positron decay process in order to produce beta. So we are able to observe either electron decay or electron capture process. Okay, so we get to know much detail about this later. So we now moving to section called internal conversion and Auger electron. So what is internal conversion is that what we have discussed is that while electron capture, there is an because electron is captured from the orbit, right? So electron is captured from the electron orbit that is nearest to nucleus. So before that, all the alpha decay, beta decay we have discussed about it, basically focusing on all the processes happening related to nucleus only. Now in the electron capture process, the electron is captured from the electron orbit near to the nucleus. So in that process, as the atom get excited and de-excited, we will be getting a gamma ray. So in some cases, you will be having excess energy. Okay, along with that gamma ray emission, there will be excess energy. Such energy can actually knock out an electron from the nearby electron orbit. Okay, so such a situation, for that case, there will be a huge requirement of the energy should be more than the binding energy of electron in the orbit. So if you have a energy that is more than the binding energy of electron, you can remove that electron from that position. Like if you see that if you have larger electron energy of a orbital electron, so it can actually knock out this electron from this position due to internal conversion electron. So that is a process. From that internal conversion electron, here you will be having a vacant space. Okay, so internal conversion means if you have a sufficient energy after beta decay in the electron capture process, this electron from this position can be knocked out from that position and can pull out from the atom. So such electrons are called internal conversion electron. So if such case there is a vacancy will be there. So from the higher shells, so electrons can move from this M to K or L to K sometimes. So it's mostly happening from M to K. So there will be a orbit can the electron in this M shell can move to the K shell. In that case, there will be a X-ray emission will be there. So such transition can emit X-rays. Okay. So from a higher shell to lower shell transition of electrons can emit an X-rays. Okay. Sometimes these X-rays can be leave as a photon. So it can leave atom as a photon. So we can collect X-rays from that emission. So you may get gamma rays, X-rays, internal conversion electrons. Also, in some case, X-rays can be stand within the atom. So X-rays are after leaving the photon, or we can within the atom. So if X-ray have the enough energy to emit an atom from the one of the orbit, here you can see the one of the orbit, it can emit an atom from the orbit. Such electrons, such a knocked out electron by an X-ray can call Auger electron. So after this transition, there is an X-ray observing. The X-ray can either leave the atom as a photon. If it exists within the atom, if it can knock out one electron from the orbit, such electrons is called Auger electron. So that's about internal conversion and Auger electron in the case. So in our all discussion, we have discussed about different process of alpha decay, beta decay, and gamma decay, and production of neutrons. There are many other processes also we have seen to produce neutrons, like in electron capture also we have produced neutron. In other case we have produced positron decay also we have produced some neutrons. So many processes are there to produce neutron. Also we didn't discuss about much about proton decay. So proton decay normally difficult to occur naturally, but it happens using accelerators. So also there are radioisotopes. After bombarding with heavy particles, also you can produce these all subatomic particles. Radioisotopes is some other case where you can make the particles. There is one more process we have to discuss, is that it's about beta delayed proton emission. That means some cases after beta decay there will be emission also proton also. Such process is called beta delayed proton emission process. So just to note it about, that's a process when we have a beta decay, delayed beta decay proton emission process. And radioisotope is one of the radionuclides where you can have chances of producing the subatomic particles with some controlled machineries or accelerators. So of course accelerators are the where we have to produce neutrons and protons. Of course we'll discuss those things later on. Then finally we need to define general reaction forms. We have discussed many reaction forms, right? So in that we have tried to identify a general reaction forms for alpha decay, electron capture, positron decay, gamma decay, then proton emission. Okay, so we have a general way of representing all the reaction. We'll just take an example before. Now we can identify how do we produce a alpha decay. So here we'll be reducing losing 2 neutron plus 2 proton. So we'll be having a decrease of 4 and 2 from here. Then we'll be getting alpha. In the electron decay process, we'll be getting neutron addition, proton addition. In addition to that, then we'll be getting an electron. Then we'll be getting electron capture. In that we will be neutron less amount will be there, but the same number of n plus will be maintained. And again in the positron decay we'll be having a proton will be less, but additionally we'll be getting a positron plus a neutrino. Then we are having a gamma decay. There will be no change in the atoms in this case. So but it is de-excited from an excited state to a ground state, producing a alpha ray. So these two are particles. Then here we will be producing a gamma ray. So in the electron capture also we are producing a gamma ray that we have to note it. And in the proton emission we have to in the beta delayed process, actually we can produce a proton emission by getting a beta delayed process, proton emission process. So this is how the general reaction form from all the process about radioactivity. So we just basically addressed the radioactivity process and radioactive decay process to produce different particles, alpha particles, gamma rays. So that's how we have dealt in this lecture. Of course, there are ways to produce much using radioisotope and all that we will discuss later. On the next lecture, we will be discussing about decay and much details of radioactive decay processes, and we will be addressing naturally and occurring and artificially occurring radioactive sources. Hope this lecture find useful and try to understand what is general reaction forms and what is the different types of reaction process to create beta alpha particle and gamma rays. Okay, with this I'm just concluding this part of the lecture series. Okay, thank you once again for listening.